Hello, everyone. This is Spencer Snowling from Hatch, and I'm glad that you could join us today for the GPSX webinar for July. So I'm here today to talk about modeling industrial wastewater inputs to municipal water resource recovery facilities. So the idea behind this webinar is to talk about municipal plants, but then talk about when you get some sort of delivery or something comes down the collection system that is from an industry and it's a little bit outside the normal range of normal wastewater. And, what are the things that you have to think about when you're setting that up in your GPSX model? So the plan for today, I always want to encourage everybody as well to take advantage of the question and answers panel or the chat panel in your MS Teams window here. Put down any questions that you think of as I'm going along through the presentation today, and I will stay around at the end of the webinar after the final notes there, and then I'll stick around for a bit and answer as many of those questions as I can. All right. So my plan for today is to go through just a little bit of background about industrial wastewaters and waste streams that might be coming to your municipal plant. And we'll talk about characterization of those wastewaters. We'll talk about how you can set up dynamic wastewater flow into your plant that's kind of representative of how things might start and stop over time. And then we'll spend a bit of time talking about the relevant biological and chemical mechanisms in the Mantis 2 biological activated sludge model that we have, and those that are relevant to high strength wastewaters. And then finally wind it up by talking about sort of the most advanced application, which would be to customize one of our user-defined components and to sort of take advantage of those customization features and create your own component that will then have an effect on the system. So I have 4 desktop demonstrations lined up for you today. And as I mentioned previously, please feel free to put any questions that you like in the chat and or questions box, and we'll get to them at the end. Okay, so just to reiterate again, I'm not talking about modeling industrial wastewater by itself, so not dedicated systems, but rather I'm talking about running a model of a municipal wastewater system, and seeing how that it can be affected by suddenly having a large COD load with low nutrients in it come to the plant, and how you would model that and what useful things you can do with that system. Now, having said that, I will note that GPSX is used all the time for modeling dedicated industrial wastewater systems. In fact, we have our Mantis IW library that was specifically developed for refineries, for petrochemical industries, and we have lots of other experience using GPSX for industrial applications of many different kinds. So I was talking to my colleagues here. I think we're going to do a whole separate webinar that's just dedicated systems for particular industries. We'll do that one down the road. But so today is just municipal wastewater that's got shots of industrial stuff in it. Okay, so the original ASM type models, ASM1, ASM2D, that whole structure that we've adopted and developed in GPSX, these were developed back in the day in the 80s and 90s around the concept of municipal wastewater. So the calibrations of those models really reflect those types of inputs that are there. So now that means, of course, that it doesn't mean that you can't use it for industrial, but that's where the calibration starts from. So now our Mantis 2 biological model that is the standard, is the default that you're using when you start GPSX and put stuff on the drawing board. That Mantis 2 model is primarily also based on municipal wastewater, but we have lots of good experience with using it for municipal facilities that are receiving industrial types of input. And particularly, I've done quite a lot of work in food processing waste over the years, potatoes, wineries, breweries, those sort of things. So I'm going to talk about that, tell a few little anecdotes and stories along the way today. And so that's there and available. You can use Mantis 2 for this type of situation. So industrial components, they can be really challenging, really a significant aspect of what's going on at a wastewater facility. So they can be very challenging to characterize and quantify, partly because they're very inconsistent in a lot of experiences that I've had. So these industrial inputs can be very high in concentration, with intermittent and unpredictable volumes of flow. I've talked to many, many facilities where they're like, yes, we have a brewery in town. We don't know when the big slug of COD is coming to the plant. Sometimes they let us know ahead of time, but sometimes we don't know. It just happens. It's very unpredictable. So these wastewater inputs from industries can often have unusual compositions compared to regular municipal wastewater, such as extremely high or low nutrients in comparison to the COD. So a couple of the examples I'm going to show you today reflect a situation with a high COD with low nutrients in it. They also can be of varying biodegradability. There's lots of projects that I've worked on where we've made assumptions about the biodegradable nature of the particular food waste coming, and sometimes we were right and sometimes not. So today's webinar, we'll be discussing all the important things that you need to keep in mind when you're setting up a special industrial influent on your drawing board for your municipal plant. So I'm going to talk about how to do the concentrations part of it, and I'm going to talk about how to do the flows part of it. And as with any modeling exercise, the more information that you have about the influent, the better. So, and I'm going to hit on this many times in today's webinar, influent sampling, doing some characterization is really, really important. I know it's also very difficult, but it is important to be able to have at least an understanding of what's happening. Okay, so each and every industry's wastewater is different. And in fact, it can actually be very different if from the same source over time. So I mentioned potatoes. So I had this project that I did many years ago with another client where there was waste that came from a potato processing facility. And so, for example, right after they harvested the potatoes and they were producing French fries, the waste had a certain type of characterization to it. But as the year went on and that sort of stack of potatoes kind of aged over, the time as they were using them up, then the amount of potato that got removed before they could get to the inside part and make good French fries with, that part kind of increased and changed over time as the potatoes aged. So their wastewater therefore changed quite dramatically from right after the harvest till when the pile of potatoes ran out. And so we included that in the model. So there's also difference in the wastewater that might come from a food processing facility under different, production schedules. When you're making, rice products, that's going to have one kind of wastewater. And if you're making pasta, that's going to have a different kind of wastewater. These are things that you would hopefully want to have an understanding of. And also the cleanup phases after there may be a downtime where they're switching between products and they're cleaning and the cleaning agents are coming to the wastewater as well. This can cause the system to have very extreme swings in COD concentrations, the amount of nutrients, the pH, the alkalinity, and so on. So, and they can also have particularly difficult components to deal with as well. So the one obvious one from food and other types of food related waste is fat, oil, and grease, fog, being that might be coming through your collection system and it might be impacting your particular facility. Metals can also be part of this as well. They might be present. They might have an impact. I threw fish scales on here. That's another project that I had where the client was telling me all about the fish processing facility, how fish scales are really difficult to deal with in that particular activated sludge system. The fish scales themselves are kind of slowly biodegradable, so they're kind of hard to treat and they stick to everything, and they are also neutrally buoyant, so they didn't either float or settle out. And it was really interesting story, really interesting, although difficult for them to have to deal with. So for modeling purposes, when we want to set something up, we want to have a representative characterization of that incoming waste, right? So we need to know at very least the COD, the nitrogen, phosphorus, and pH. There could be many other aspects and components that are there, but that's kind of like the minimum thing you got to know. So now if, as happens quite a lot, there is some pre-treatment at the source, at the place that's producing the wastewater, if they then treat it before releasing it to the sewers, to the collection system, you should, of course, also characterize your incoming waste with the pre-treatment in place. So there is, as I mentioned earlier, possibly many different characterizations depending on what they're making. As I mentioned, you might get something different for pasta than you would for rice products, and also what's going on during the cleanup time. So all of these things kind of add together that your characterization of that waste coming in likely does change over time. So in GPSX, the place to start is with whatever data that you know. Let's put it into the Influent Advisor tool in GPSX and sort of establish an average loading. And I'm going to come back to that and show you a demonstration of doing a typical one here in a moment. Okay, now I'm going to touch on many different kinds of industrial wastes here, and I'm going to make some, and I'd like to make sure I'm clear on this, very broad generalizations. You know, as I've been indicating, you know, the industrial wastewater is very variable. So I'm going to have some wide ranges of numbers here. So food processing waste, by that I mean wastewater that comes from a factory that makes some sort of food product of some kind. These are usually thought of as being readily biodegradable wastewaters, but to be honest, my experience has been surprising. It's not always the case. We had a project about 6 years ago where we were having, it was a regular municipal plant here in Canada. They received waste that was coming from a pasta making facility. And I was really surprised actually how not biodegradable the wastewater from the pasta place was. It was not completely inert, but it was not as super readily biodegradable like I maybe would have expected. So the CODs in these kinds of wastewaters could be hundreds to 10,000s of milligrams per liter range. These are also, as I mentioned, depending on the product, depending on how they process the food, what they're doing, any pretreatment that they're doing at the plant. So any other ingredients that they're making into the particular product that they're making, you know, fine starches and other fillers and things that coatings that go on to fish sticks and other things, you know, these can be a little bit less biodegradable maybe than the actual food parts itself. So I briefly mentioned that fog can be an issue. You know, again, I've also been involved in some meat processing facility type modeling projects, and absolutely it was you know, the number one pretreatment issue was to handle the amount of fat that was coming into that system. And also nutrients can also be very high in these. So in the meat processing project that I was just mentioning, it was an MBR system actually, and so in that particular case, I was really surprised when we started getting involved in calibrating that model. You know, the incoming ammonia was like 800 milligrams per liter. It was really quite up there, and it was mostly from the blood, you know, from in the tissue, the amino acids and other things that were there and present. You know, when they break down, they really have a lot of nitrogen in them and high concentrations. And also, I will mention, again, sort of anecdotally, that some places too also use washing or cleaning agents that are there that happen on a periodic basis. I know, for example, breweries are doing this, that also could potentially have a lot of phosphorus in them as a, you know, kind of a soap or a surfactant or something. And that can also, of course, go right down the drain and into your wastewater treatment plant as well. So there's a whole bunch of unknowns that you might want to keep in mind. Okay, so when we get around to the brewery waste, it's also biodegradable. It's maybe not as quite consistently as high as concentration, but you're looking at probably hundreds or thousands of milligrams per liter, can have significant solids, can also have pH issues depending on what they're doing and what they're making at that particular facility. Winery waste is also very much the same. You can also have hundreds or thousands. We did a project actually at Hydromantis back about 10 years ago, and in that particular case, there was a lot of solids in this particular waste stream. It included the skins of all of the grapes and the stems and everything else that basically wasn't the liquid that they squeezed out of it. And that particular slurry of stuff had like I think it was almost 500,000 milligrams per liter concentration to it, and that was brought to a municipal plant. In that particular case, put in the digester. So. And also winery waste does traditionally, again, maybe not always, but it does have issues with having lower pHs as well. So, you may want to also characterize that properly when you put it on your drawing board. Dairy wastewater, I haven't had nearly as much experience with that, so it varies. I know that the concentrations vary greatly depending on the product being produced. So for example, cheese will give you a very different wastewater than producing yogurt. And so on. They vary very significantly in BOD and COD concentrations, and even in the BOD to COD ratio for a particular facility, and also pH. I actually, in preparation for the webinar, came across this really fantastic paper, and I'm just posting a table of characterizations and measurements of industrial wastewater from different dairies, depending on the different kind of products that they used. I've put the reference for this paper over on the right-hand side there, so you can always pop back and watch this video and grab that reference and look at it. It was actually quite a good paper. But look at this here. This is pH, just for an example of the variability across these different types of products. This is the effluent pH from facilities producing these types of products here. And you can see the pH is like, 4 to 11 and 7, 5, 4, 12. It's like absolutely all over the place. Even the cheese here, just from one type of product, range from 3.4 up to 9.5. So it is, again, super variable, all over the map. And even these concentrations here for BOD and COD, these are ranging over at least an order of magnitude or two as you go throughout this table here. And so you can see that, there's a lot of variability involved in these sorts of things. I'll touch briefly on pulp and paper as well. Now, again, sort of generally, as a whole, thought of being somewhat less biodegradable. It really depends on the product that is being produced and what the source materials for that paper is. So if you have a pulp and paper mill together, so that means, of course, that the part of the plant is producing pulp, that has a certain kind of wastewater, and making the paper has its own other different kind of wastewater. Or if it's paper that is being made from, pulp that has already been manufactured or recycled from another source, then that has, a different kind of wastewater. So I was worked one summer when I was in high school in a paper mill that was working from recycled paper. So a lot of these pulps are, of course, bleached in order to get you white paper, and they have a lot of fillers in them as well. So these things have a huge effect potentially on the concentrations that are in there, what is actually in the wastewater, what the pH is going to be. There's lots of different ways of making paper that have both basic and acidic type approaches to them. So the wastewater can be, as I said, all over the map. Okay, so in general, beating this dead horse again, yeah, wastewaters are extremely variable, and the loading really depends on a lot of factors: what the production schedules are for the products that they are making, how they go about doing their cleaning and maintenance, and what they might use to be able to do that. So you may have flows that are starting and then stopping, and maybe they don't work on the weekends. Their cleaning schedule might send out its own different kind of wastewater. Also, the source materials, like for example, the pulp that I was just mentioning, and actually the source water, which I haven't even mentioned up to this point. The source water itself, if you were making products from groundwater, it might have a different alkalinity than if you were using surface water from a lake or ocean water that might have a lot more things in it. So basically, there's a lot of things to sort of keep in mind, and then therefore, getting data on that industrial waste stream is essential. So you're going to want to get, for sure, at least the flows as you best understand them, the concentrations of those things that we discussed earlier, the pH, an understanding of what the pre-treatment is doing and what it's supposed to be there for, and the expected timing. And again, nobody knows. Sometimes it just happens, but nonetheless, an understanding of what to expect would be helpful. So what you would normally want to do then is take that data that is from this list and things that you do know, and then we're going to put it in Influent Advisor in GPSX to understand the data, make sure that it all makes sense. And what is going to happen is you're going to enter in the COD and the nutrient concentrations, like TKN, for example, at the top of the left column, and you're going to enter pH and alkalinity and everything else that you know. And what is likely to happen if you have a high strength wastewater is that you're going to have to adjust the stoichiometric ratios away from the defaults that are there for the municipal wastewater. So by that, I mean these variables here called FRSI and SS and so on. These are the breakdown of how much of the total COD that you have entered is soluble inert, how much of it is readily biodegradable substrate, and how much of it is particulate material, and so on. So you're very likely to have to change those. You are also very likely, especially if it's very high concentrations, to have to change the N and P fractions, the nutrient fractions of that inert material, in order to make it work. So these are set here for municipal wastewaters. They're like 5%, like in other words, 0.05 grams of nitrogen per gram of COD is kind of tied up in the COD itself, in that soluble inert material. You may find you have to set those to 0 to make everything balance out okay. And what we're going to be doing is looking for the red numbers that are there that indicate a problem when you enter them. As you're entering in your data into Influent Advisor, if you see red numbers like this pop up, it's almost always going to be a situation where you get a negative number. So that doesn't make any sense. We're subtracting something to get a value here, and you come up with something negative. That's when you got to go back and adjust your stoichiometry. I will mention that we have an entire webinar on how to use Influent Advisor to characterize your waste and to understand these sorts of problems. And so I'll just mention that here. You can pop over to our YouTube channel and take a look at that. Actually, I got quite a few of those links to other previous webinars in today's presentation. Okay, first demo. Let's take a look at characterizing a very high COD wastewater. This will be just a very simple explanation of what it looks like when you are doing that. So this is a typical setup that you might have here. I've got some regular base municipal wastewater coming through the collection system, and I've got this industrial thing. I'm going to set the flow to 0 to start, but I want to characterize it so that I can turn it on for periods of time. So the way you would do that, right click here, go to the composition menu, go over to Influent Characterization, and it pops up this menu. So if you are a GPSX user, this is just sort of your standard Influent tool. If you're new to GPSX, you may want to go watch that video. It explains everything that you might want to understand about how to use this tool. It's essentially like a spreadsheet. You enter in all the information you know in the left-hand column, and it sets it up and calculates the state variables and calculates everything else that the model needs in order to proceed along with the dynamic mass balances. All right, so what we are going to do is enter in an Influent total COD of 8,000 here. So this is taken from potentially a concentrated dairy waste where we have a large COD compared to the nutrients that we have here. So I'm going to leave TKN and total phosphorus at the values that are here, and I'm going to change this to 8,000. Okay, so immediately we can see that what happens is that we are having some variables that are coming out negative. Now, the way that the reason that they might be a negative value is that often we calculate what some other last component in the mass balance of all of the nitrogen. We calculate it by subtraction. So we say, okay, of this total amount of TKN that we have, certain amount of it's going to be ammonia, certain amount's going to be tied up in the inert materials and so on, and whatever's left over, we're going to stick in soluble organic nitrogen. Well, if that happens, that we don't have this balanced and set up stoichiometry very well, this can come out negative. And so just to go back to the slides, you may remember that I said some of these fractions are things that you're going to have to change. And as part of that, one of these things that's typically you have to do for very large values of influent total COD is probably set these to a lower value than you would get in a municipal plant, or potentially 0. So I'm going to set these to 0 now. And if I enter these two values and do that, we can see right away that cleared up our problem with the nitrogen. So now it's saying basically it's going to have the soluble organic nitrogen is not being affected by the amount of total COD that we have. So that 0.05 times this number is probably bigger than 40, right? So it's that was what was happening there. And it's the same thing for phosphorus as well. So 0.01 times 8,000 is a non-insignificant amount of phosphorus. So we are going to set these to 0, and that will in essence clear up our remaining problem that we had for mopping up the remainder of our phosphorus. Right. Okay. So then you would move on to the next step, which is to, change the biodegradable fraction and the inert fraction and so on here. These are very municipal based numbers. So I think typically we would probably expect, like, say it was a very soluble one, we would have something like this. Maybe 80% of the total COD was soluble substrate. I'm going to remove the colloidal, remove the inert fraction, particulate inert fraction. And we can see here that that's now pushed us into maybe a more regular value of BOD here. So we can see it's 8,000 COD, and over on the right-hand side, 5,200 for BOD. If I really wanted to make it, very, very biodegradable, I could even make this 0.95 here. And then push this up BOD up a little higher. If you really want to see where all of that COD is going in terms of state variables, you can open up these other soluble organic and particulate compounds here. We can see that basically almost all, basically 95% of this 8,000 is going into readily biodegradable substrate. And that is very likely a good way to put it for something that was, a very biodegradable food waste coming into your facility. Okay, so that's basically just pointing out to the various parameters that you should keep in mind when you're setting that up. Okay, back to the slides. Okay, so that's a very quick summary of the important things you need to think about when you're doing the concentrations part of your influent. Now we want to talk about modeling the flows part of it. So we want to say how much is going to come in over a period of time. So now how you do this is really dependent on what you're trying to achieve with your model. If you're really only doing steady state simulations, then you can use some sort of average loading that is a representative of how much flow do I get in a day and put that in for steady state, and that's fine. That's all pretty straightforward. But the more interesting and I think more valuable part of it is when you get to seeing those short-term effects of a COD peak coming into your plant. It does require dynamic simulation. I want to see what's happening in the morning versus the afternoon versus midnight, see how those things change over the time of day. So therefore, you need to set up and characterize an influent for the industrial part of it, and then have it off, and then turn it on, and then turn it back off again, and so on. So I have some examples set up of that type of a thing here. So, and typically the way that we do that is to have a regular influent representing your regular wastewater coming into the plant continuously. You would then set up another object here that represented the industrial wastewater, set the flow to 0, do the characterization just like I was showing, and then you can set the flow of this up for a while and then down for a while, or turn it off, or whatever it is the pattern is that you think is relevant for your particular industry that is contributing to the wastewater. Right. So if the industrial wastewater flow that's coming in is a constant, then you can just use an influent object like that one that I was just showing there. But for dynamic flows where things starting and stopping over time, there's a couple other options that you have. We could use the truck object, which I'll show you here in a moment. We can use an influent object combined with the flow timer or scheduler process control object that you could put on the drawing board next to it and hook that up. You could also read a schedule of influent flows from a spreadsheet using the file input controller. And then you can also write a custom algorithm to calculate the flow based on some other things that are going on in the model, or generate some random input, or many other types of things. Once you're at the point of writing code, you can kind of do whatever you want. Okay, so I'm going to touch on each of these there fairly quickly. So this is the truck object. So basically you set up a schedule in the truck deliveries, and that is repeated the same pattern every day. And so you can say, I want to have a number of individual deliveries here. You specify what the volume is of the truckload that is coming in, when the dumping starts and when the dumping ends. And every day it will do exactly the same thing. You can also do that same concept, but with a little more sophistication, by putting in a regular influent object and then dropping one of these process controllers. This is actually a scheduler. Put that onto the drawing board, and then you can do other interesting things here. You can break down the entire week's schedule into chunks and then do different things in each section. So here I've broken the whole week out into 8-hour shifts, so to speak. And then during those 8-hour shifts, you can schedule when you want that flow to be on or off. So for example, what I've got set up here is a system where basically there's no dairy waste coming in except for 8-hour shifts on Monday, Tuesday, and Friday. And so that's a nice way to sort of do something that's a little bit realistic. And in this case, it would sort of repeat the same thing week after week. The scheduler is a very powerful and very flexible tool, so you can do really, really interesting things with it. So using the scheduler or the flow timer or any one of these other control units is actually covered in great detail in one of our other webinars from a couple of years ago, Advanced Process Control with GPSX. And so pop over to the YouTube channel and take a look at that. Okay, so another third option was to basically set up a dairy waste here and read the flow in from a spreadsheet. So that's something we do very straightforwardly. There's a tutorial on how to do that. And then lastly is writing a custom algorithm to calculate the flow based on something else going on in the model. So you might write a little bit of code in our user macros section where you can say, if the day of the week is Monday, Tuesday, or Friday, then I want the flow equal to be 500. Otherwise, I want it to be 0, et cetera, et cetera. So we actually just did a webinar on that. The last month's webinar in June was basically about doing this kind of code writing. So pop over there and take a look at that when you have a moment. Okay, so let's take a look at an example where we're going to use the truck method to make that happen. So I'm going to pop over to my next demo. Okay, so just very quickly to explain here, we've got a regular activated sludge plant. We've got a regular influent coming in, and we've got the truck set up here. So if I go to the characterization, it is set up with some not terribly strong wastewater, but a little bit higher than regular. This is that same influent panel, works in the truck is exactly the same way it does in the regular influent. And then as far as flows are concerned, we have 2 truckloads coming during the day, and one of them is from between 6 and 7 a.m. and then the other one is in the afternoon between 2 and 3 p.m. And so during that time, some flow will be delivered to the plant. Right. Okay, so what I'm going to do is I'm going to run it once without any truckloads so that you can just see what the regular performance looks like. So we're going to let it come to steady state here first. And then let's see here. Okay. And then now we're proceeding along on a 2-day simulation here. You can see all these bars going up and down that represent the performance there in the activated sludge tank. So as far as effluent is concerned here, I'm just showing you ammonia in green along the bottom, and here in red is the total BOD5 coming out of the effluent over here. Okay, so that's what a typical day looks like. So now let's add in a delivery of, say, 1 or more trucks come between 6 and 7 a.m. and they bring 60 meters cubed to the facility and dump that off. And then let's say in the afternoon, we get a total of 35 meters cubed coming in the afternoon. So if I run that again, the GPSX will take care of figuring out the right flow rate to get that amount of cubic meters into from the truck and into the system in the given amount of time that you've specified in the schedule there. So now we're doing our 2 days again here, and we can see very clearly there's one spike from the morning one, and here's one spike from the afternoon one. So now this spike's pretty bad because it lines up exactly right on where some of the early morning diurnal peak was. So maybe I could move that a little bit later in the morning. So let's move that from 10 to 11. And then run that again, see how that looks. So, you know, these are the types of interesting analysis you can do with GPSX, is to move these schedules around during the day to sort of evaluate what might happen at this particular facility under these different scenarios, right? It's a what if scenario. Right. Okay. Well, it moved it over to the right here. Now they're a little closer together. It certainly did not make anything better. In fact, it may have made it a little worse, actually, because we're now doing it when we're already up at the high peak there. Okay, so maybe it would be better to say, well, if I want to keep my effluent BOD under 6, this line right here, then probably I can't accept this much load. So you could do a capacity analysis here. You could say, what is the amount that I can actually accept and still be in reasonably good shape here? So we are going to reduce these down to 25 each, and then run it one last time here. And we can see where we end up. You may have noticed, by the way, the ammonia is always in really good shape down here. So, all right, well, we're not exactly under 6 all the time, but most of the time. If you did a composite sample on this, it would be below 6. So that's not a problem. So, all right, so it basically is a nice way to sort of look at doing intermittent slugs of COD that might have an effect or bring some extra loading to your plant, and see how scheduling them at different points of the day can help out the situation. Okay, back to the slides. All right, so that's how you do concentrations. That's how you do your flows. Now, the last thing is I wanted to talk a little bit about the relevant biological and chemical mechanisms in the Mantis 2 model that kind of come to play when we get into working with these kinds of concentrations. So the Mantis 2 biological model, yeah, it contains a few mechanisms that are relevant for very high strength wastewater inputs. One of those is nutrient limitation on biomass growth. That's a common thing. Of course, you have lots of COD, maybe not so much phosphorus or nitrogen in it. That is going to play a role in understanding and seeing what's going to happen. And I have a nice example ready to go for you here. There's also the inhibition from high concentrations of free ammonia and free nitrous acid in there. So I'll show you how those work. And generally, there's actually the whole ability to add pH inhibition to any one of the biomass types, actually. Okay, so let's talk about the nutrient limitation. This is a feature that I believe it wasn't in ASM1, but starting with ASM2, I believe they had proper nutrient limitation as part of the growth calculations for all of the biomass types that are in those models. So now we have it to actually quite a sophisticated level in Mantis 2, but it all works in kind of the same way. So if you look into the details of these ASM type models, the growth of most biomass kind of looks in an equation like this. You have a growth rate term here, the growth rate term times the amount of biomass that you have, times one or more of these type switching functions that are there to sort of turn off the growth when something runs out. So these are actually a really elegant and very nice way to implement those wastewater aspects in a very mathematical, nice and easy to solve format. So if you haven't seen these before, basically this is SS is the soluble substrate. This is the food. And this is part of a term that will range between 0 and 1, and it's designed to go to 0 when the food runs out. It basically then turns off the growth. So if the soluble substrate is very much larger than Ks, then we'll proceed along as normal. However, if we find that S falls below the Ks value, then it will start to go to 0, and then that means this whole thing stops. Now, this is written for food, but you can do the same thing for anything, right? So here we're saying, here's our growth rate, and then it's got 4 of these types of saturation terms, and this is oxygen and substrate, and then you can do your nutrients like this. This is for ammonia, and this is for phosphorus. So basically, it's saying that if we're missing any one of these components, if we run out of ammonia or we run out of phosphorus, then that basically means the whole growth stops. If one of these things goes to 0, then the whole thing is 0. And so that's a very nice, excellent way to do that. And then you can use these particular parameters to control the sensitivity to that particular component and running out of that sort of thing. So, for example, this parameter controls how sensitive the system is to running out of nitrogen, and this one is for how sensitive it is to running out of phosphorus. And all of those parameters are available for you to take a look at. If you right-click on any bioreactor, go to the kinetic menu, and then open that up. And this is a very long and detailed menu, if you've ever investigated it. But I have it open here showing the heterotrophic biomass, which is at the top of the menu. There is the K term for using phosphorus as a nutrient. This is a different type of sensitivity, sorry, a different types of saturation term than we are when we get into doing EBPR. This is purely just for the purposes of doing it as a nutrient. So here you can see that at 0.01, so we have to get to very low levels of phosphorus before it starts to impact the growth. And then here's for the nitrogen side. Now, this is actually a little bit more complicated than what I showed you on the previous graph. The reason for that is that we've added a fairly sophisticated level of nitrogen limitation here. So basically, it's going to go for ammonia first, but if ammonia runs out, but there's still nitrate around, it'll switch over to using nitrite and then nitrate. So basically, there's a couple of parameters that control how all of this happens, but the concept is the same. Once it gets low enough, once you've used up all the nitrate, all of the ammonia, and then you switch to nitrate and used up all the nitrate and there's no TKN left, then of course it says, okay, well, now I don't have anything for nutrients and I'm going to stop growing now. Okay, so that's how that works. And so I'm going to show you in a few moments here an example of that in action. But I did want to touch on those other two topics here, the inhibition. So this is for free ammonia and free nitrous acid. And they are exactly the same type of term, except that having the K on both the bottom and the top. That makes it an inhibition term. It's basically just flipping this all the way around. So basically we are now turning on the growth, turning off the growth in the presence of something instead of rather the absence of something. So these things are basically designed to say that when we have a large concentration of non-dissociated ammonia and nitrous acid, then that's going to cause an issue, and this is how we implement it in our model. There's actually a whole lot of other brackets and saturation and inhibition terms as well, but I just simplified it down to this to show. And please note that this is the non-dissociated form, so this thing here is actually dependent on the pH. So there's even that extra level of complexity going on here. So for the same ammonia concentration at two different pHs, you would have two different amounts of inhibition going on. So it is this function, by the way, that allows people to make nitration happen. If you want to do it with pH control, to take that first nitrification step, but not the second one, and end up with some nitrite. You can do that with some pH control if you're doing it at very high concentrations, say like right after it's been through a digester. Okay, so those terms are exactly the same kind of deal. They're here on the menu. So you can see in this case, it actually works the other way in terms of the magnitude. So for when you're doing it sort of running out of nutrients, the higher value of that K value means more sensitive. But here with these inhibition terms, it's the other way around. The lower the value, the more sensitive it is to the presence of this particular thing. So you can see here what it's saying is this particular calibration is much more sensitive to free nitrous acid than it is for free ammonia, because that's a much lower value. And you'll note here we have different values for the AOBs and the NOBs. Okay, and then lastly, we have a sort of a generic across-the-board pH inhibition that can be applied. This is normally turned off by default, but you can come in and turn it on by clicking in the Site Properties button in the upper left-hand corner of the drawing board. You can click down here and hit pH, and then what we do is, on top of every other calculation that we're doing for growth, we apply this thing and tack it on to the end. And it is basically a relationship that allows you to specify what happens at various pHs. So we just take whatever number this is. It goes between 0 and 1. If you're in this middle range here, it's always equal to 1. So basically, you're multiplying by 1. There's no effect. But if you drop off down here to the pH of 6, then this is half, meaning it's going to run at half speed. By the time you get down to 5, then it's going to be running at 0. So it's going to turn off any growth at all at the lower pHs. So I don't tend to use this particular feature all that much because we already have the other really relevant stuff already built in. But if you're working with something in particular that you want to implement, you can come in here and turn this feature on. Okay, so I'm going to show off my third demo of the day. We're going to look at a high COD loading, a dynamic simulation, and we're going to engage the part of the model that is going to do nutrient limitation. So we are going to have a huge amount of COD come in with not very much nutrients in it, and we are going to run out of nutrients. And basically what we're going to do is we're going to work from this scenario that I set up with high COD and low nutrients. So if I click on this tab here, we can see that here's our 8,000. That's actually where I got the number for the previous example. We're saying that we have at 8,000 milligrams per liter of COD, but only 10 milligrams per liter of TKN and 1 milligram per liter of phosphorus. So this might be something that you get from, potentially a food processing facility, high concentrations, but the COD to nutrients are out of whack. So what we're going to do is we're going to run it once here, and it's going to be a 3-day dynamic simulation. Now, if you look at this thing right here, it's showing that the wastewater influent flow coming in is equal to 0. But we're reading this in from a spreadsheet. So at about 2/3 of the way along here, this pops up. Oh, I just missed it there, but you saw it. It popped up to 25 milligrams per day, meters cubed per day. And that was showing that we're feeding something in, 250 meters cubed per day, feeding that in at that rate for a period of time, and then it goes back to 0. So this is as if the factory was turning on for the day and it did an 8-hour shift and produced some wastewater and then turned off again. And then maybe it wasn't coming back on with production for another couple of days. So that shot right in the middle of the day. The regular flow of the wastewater is the regular diurnal pattern. Okay, so what you can do then is we can take a look at what's going on in our effluent. So I'm going to blow this up so you can see it a little better. This is the effluent, BOD, and COD. And you can see that with this huge contribution here, we got a lot of effluent, a big spike in the effluent. So now there's multiple things kind of going on here at once, right? What we're seeing is that there's a lot of growth happening. It's sort of a lot more food coming in. And now we don't have a DO control around here. We've got lots of air, but it's a limited amount of air. So that's sort of maxed out as well. And you'll note here, if I look at the effluent nitrogen, we can see that both the ammonia, it's on a little bit of a small scale here. I wanted to keep these on the same scale. You can see it goes to 0, and this is the nitrite and nitrate added together, and you can see that goes to absolute 0. Like if I click right here, you can see it's like 0.001. So basically, this is showing nutrient limitation. When this hit the ground, when that huge amount of COD came in, there was a lot of growth that used up all the excess ammonia that it could get its hands on, moved over to nitrate, used all that up as well. And then at that point, it couldn't grow anymore. And so what you are seeing here is a combination of the lack of air, because it actually did max out our aeration system too, but also it completely used up all the nitrate and all of the nitrogen. So this is kind of a cool and interesting thing to play with. You could maybe make up different scenarios where maybe you paced out that flow over time, did some equalization or something. You can see how the effect of the distribution of that term, that period of time, what's going on in there, and you can dig through the details of the model to find out what's happening. When I was setting up this example, I was actually playing around with a menu, and I'm just going to point it out to you in case you're a GPSX user and you've never really dug through this one. If you go to the output variables menu, these two menus are kind of like some internal variables that we are calculating along the way. And they actually can be quite interestingly diagnostic. So in the rates section here, you can, for example, look at all of these different processes that are going on. So growth of a heterotrophs on all these various kinds of substrate, and anoxic growth, and growth of all the different kinds of other biomass, and so on. And then also here, you can even dig into this internal variables menu if you really want to find out some of the other details. These are some calculations that we are doing as part of the overall mass balance, but sometimes they make for interesting things to plot as well. So you could, for example, look at the total nitrogen that is available to be used as a nutrient for, take a look at what happens to that over time. So what I did was I just put the regular aerobic growth of heterotrophs on soluble substrate. I put that on a graph here. These are the 3 zones of this aerated bioreactor. And I just want to run this one more time for you because it tells the story in animated form. So you can see here that the daily diurnal pattern is proceeding along and the flow is going up and down. And then here, oh, now we've got our loading coming in, and you can see eventually the growth just completely peters out, except for a little bit in the last zone. And then it comes back to life again after the COD load is finished. So it's kind of a really kind of cool way to do that. I sort of stumbled across this. I was looking for a nice way to animate and sort of really illustrate what's going on. So if you've never experimented with these 2 menus, Mantis 2 rates and internal variables, yeah, there's a lot of really interesting stuff that you can plot there that can help you dig into the weeds, so to speak. Okay. How are we doing for time? Oh, we're getting a bit long here, so I'm going to get through this last little bit. Okay, the last step that I wanted to touch on was customizing GPSX so that you can make your own components in the industrial waste stream. So we do get a fair bit of questions about things like, how can I model PFAS, or how can I model copper, or something that we don't normally have in GPSX already. You can use our custom user-defined variables as surrogates for anything that you want. So in this case, you could do it as a surrogate for a toxic or inhibitory component. And what you need to do is to sort of specify that in the Influent, and these things will float through. We have soluble ones and we have particulate ones. You can use whatever one you want. And these are available. They're called generically soluble component A and soluble component B. So we have 2 soluble ones and 2 particulate ones. And you can do whatever you like with them, and you can write some code around them. You can interact with the biological model. So for today's example, what I'm doing is I'm taking a soluble component A, which, by the way, has SZA as its cryptic variable name. And then I'm going to apply a inhibition term like this onto our regular growth rate of the AOBs, the AOB biomass. So this growth rate here is actually, I'm going to take this growth rate that we have and I'm going to multiply it by this, and then I'm going to pass that into the model. So this bit of cryptic variable name here, this is the actual growth rate that is going to be used. So I'm going to start from my own number, and then I'm going to apply this, and then we'll see how that goes. So this is basically doing some customization. And I'm going to go to my last demo of the day. So let me start by just showing you what this looks like in terms of the code. So for those of you who attended the last month's webinar, we talked about this as well. In the user files section, there are many different files that you can adjust. I actually opened up the constants menu and I entered in some new constants that I want to be used as part of my calculation that I am doing. And so that will construct a menu for me. And then in the macro section, here's the actual calculation. This is the same one that I just showed you on the screenshot on the previous page. Basically, take the growth rate that is specified and then multiply it by that inhibition term. So now that we have that all set up, I did that ahead of time. If I go to my user menu, we can see there's custom inhibitory compound. And here's my custom menu that is made, and you can do that yourself. You can make any constants that you like, and you can build your own variables and your own menus, and you can plot your own new variables. That's part of what the GPSX customization functionality is all about. Okay, so what I'm going to do is I'm going to show you another, our final dynamic run. Basically, it's that same plant. I switched this over to being a CSTR in this case rather than a plug flow tank, just to simplify a few things. And I can see here in my industrial section, if I open this up here, if I go past the influent characterization, I can see these additional states here. This is where I can get access to setting the influent concentrations of these new user-defined states. So this is going to be 25 milligrams per liter there. Now, what I did was, just to not have too many things happening at once, I actually reset this back so that it's kind of more like normal, not quite so strong as the one that I showed you before. So it's a little bit stronger than municipal wastewater, but I didn't want to have nutrient limitation happening on top of everything else that we're trying to show here. All right, so there'll be some SZA custom component coming in for a short period of time, and then it will go away. Right. Okay. So, and again, I'm reading that flow rate again. So I'm going to run a 3-day simulation just like I did before. There's this regular influent flow, and here's that industrial waste that came on for a period of time and then went off again. So what I can do is I can plot, I can open up this menu, and just like you would plot any other concentration, like ammonia or mixed liquor or anything, if I scroll all the way to the bottom of this menu, here's soluble component A, and it was 0.2 milligrams per liter at the end of the simulation here. So you can see that in the influent, when it started, it went up for a while and it came down, and this is it's after it's passed through the clarifier and it's gone through the bioreactor. We can see it's got your typical kind of curve, a little bit delayed, of course, because it's a little farther downstream than this signal. And yeah, that's what's happening. It's this number that the inhibition is going to be based on. So let's take a look here at what happened in the effluent, and we can see that when the concentration of that component was high, then so was the ammonia, right? It's slowed down the AOB growth. Because that was at a concentration high enough to have an effect. And in fact, I used an inhibition constant of 0.5, and it did get as high as 3 here in the ammonia. So that means that it did have an effect. If I go back to the inhibitory compound, so how did this compare to 0.5? Well, it was at 1.5, so it was definitely above this level, definitely having an effect, right? Okay, so we've hit almost 3 milligrams per liter of ammonia. So let's try and actually just run this again with a different level of sensitivity of the particular compound. I'm going to change the inhibition constant to a higher number. That's going to make it actually less sensitive, right? As you may remember, I said earlier that when you have a higher number for your inhibition constant, that means that your biomass is less affected by it. So I'm going to run that again. You'll be able to see here that it is not going to peak up nearly as much as it did before, even though we have the same amount of the inhibitory thing going through. But it's noting that it's not having as high of an effect, so it was still mostly nitrifying. There's a little bit of a dip. You can see the dip in the nitrate here, as at the same time as the lack of full nitrification was happening. Right? Okay, so that's a way what you would do is if you had any particular data, you could actually use that to calibrate what this number should be, right? So if you knew that the ammonia got up to 10 or something, that would be something you could calibrate. So I'm going to reset that back to the default. And let's see what happens when we have a much stronger, much higher concentration coming in. So I'm setting that to 80, and then we're going to run that again. So let's look at this inhibitory compound. So this is going to get higher now, right? It's going to be up at what's this? This is at over 4.5. Now milligrams per liter compared to this 0.5. So what happened with our effluent? Well, it really affected it this time, and it's going to take a while to grow, all that biomass back again. We may have to run for another 2 or 3 days to finally get all the way back down to fully nitrifying. So you can see the ammonia in the effluent goes up, the nitrate is coming down because it's not nitrifying fully, and it's very interesting stuff that you can play with. So then you could look at optimization strategies or mitigation strategies in order to figure out what could potentially happen there. Okay, so getting to the end now, just to wrap things up with a few final thoughts. So as I mentioned many times, the industrial waste feeds are extremely variable and very challenging to characterize and get a good amount coming into that particular facility, both in terms of flow and concentrations. So they're sampling those things is the best way to get an understanding. So, however, even though that there's lots of uncertainty surrounding the specifications of those wastes, modeling them is still really useful. Like, I don't want to give you the impression of, well, we don't know what the numbers are, so why am I even doing this? It's actually a really useful tool to be able to quantify what the potential could be. And we find that the most useful way to do this is with sensitivity analysis, right? I don't exactly know how much of the wastewater from that particular factory is going to come to the plant, but I want to use the model to understand what could happen. Like, what's the worst case scenario? What's the best case scenario? What is the most likely thing that is going to happen? And I want to be able to quantify those. Even if I don't know exactly how much is going to come, you can still use sensitivity analysis to learn a lot about what's going on. So I'm mentioning Monte Carlo analysis here too. That's using probabilistic modeling. You run a large number of simulations. What's the percentage probability that we're going to get into trouble? That kind of thing. So we have many webinars on these particular topics, both regular sensitivity analysis and also using probabilistic design, using Monte Carlo in order to do analysis and optimization. So I suggest they take a trip through our webinars on our YouTube channel when you have a moment. So lastly, GPSX certainly has a wide range of different kinds of tools available to help you configure industrial inputs to your municipal plant and then analyze their impact in a meaningful way. But as I mentioned, quantifying those streams can be very challenging, but it's really an important step in understanding the plant performance, particularly if it's a large industry in a small town and the plant is being affected by what's coming to it.